Welcome to the today's lesson of the CBNST. In today's lesson, we will talk about solution of algebraic and transcendental equations. Equations which contains more complicated terms like the combination of algebraic, trigonometric, logarithmic or exponential forms that cannot be solved with the help of normal numerical solutions. So let's see what are the numerical methods have been given. The first method that we will be using and we will be talking today is the bisection or Bolzano method. It is also known as the interval halving method, that is based on intermediate value theorem. So let's look on this method, bisection method. Bisection method says if fx is a function, this is the function on x, which is, so there is a condition that it has to be continuous in an interval a comma b. So this thing need to be noticed, that fx needed to be continuous in an interval a comma b such that the f of a and f of b are of opposite sign. That means this is important, such that f of a, that means the value of the function at both the ends are of opposite sign. If f of a is positive, then f of b has to be negative, or vice versa. Then at least one real root will exist between a and b. So we will be taking this property, this is known as the IVT theorem. We will be taking this IVT theorem, and with this theorem we will prove or we will use the bisection method to achieve the solution of the transcendental equation. So then at least one real root will exist between a and b, and we can reach to that root by approximations. So let's say our first approximation root will be given by x1 is equal to a plus b upon 2. This is called halving the interval. So let's see how this theorem is working. Let me give you a graph. On the basis we will be able to understand the bisection method. So we can see that this is x and y axis, and we have a function, let's say, represented by this curve. So this curve is the representation of the function fx. Now you can say that the curve is continuous, so there is no gap in this curve anywhere. So this curve is continuous, and we have said that this curve has to be continuous in an interval a comma b. So let's say that this location indicates a. So we can see that this is a, and this will cut the curve at this point, and this will be our f at a. And the other value, other end point, let's say the next end point is b. So we can see that b is here, and if we use a perpendicular, we draw a perpendicular, then this will curve the curve, and this will give us the value f at b. So as we can see that at the a and b, so this is the interval, and at a the function's value is negative. As we can see that this is onto the negative axis, negative x-axis, and at point b the function's value is positive. So this theorem will be applied, or we can apply the bisection method on this particular curve, because it is satisfying the primary conditions. What are the conditions? The function has to be continuous in a comma b. So we can see from a to b the function is continuous, there is no gap in the function, and at f at a and f at b the function's sign are of opposite sign. So the function's value, you can see this is negative, and here it is positive. So that has to be on the opposite side of this particular x-axis. So that is why we can apply. So let's say if we apply this method, then what will be our first approximation method? The first approximation method is given by a plus b upon 2. So let's say we achieve a plus b upon 2, and we get this is as x1, and we can see if we do a plus b upon 2, let's say this position, this here, it comes x1. So let's say if this is x1, this is our first approximation root known as the x1. So now at x1, if we draw a perpendicular, this will cut the curve at here, and this will be f of x1. So this will be f of x1. Now we need to decide the new interval by taking this new x1 point and choosing one from the previous two, a and b. And how we will choose? Obviously by the theorem that at both the endpoints the sign of the function should be opposite. So let's say if at x1 it is negative, then obviously we will choose the other endpoint at which the function's value is positive, and we can see that is at b. So our new interval is now x1 comma b, right? So our new interval is x1 comma b. So that is here, you can see. So the new interval obviously will be either a plus x1 upon 2 or x1 plus b upon 2, the new approximation. In this case, we have seen that this is x1 b. So we'll continue the process and we'll find our next approximation. So the next approximation, that is x2, will be x1 plus b upon 2. So let's see that now this next approximation x1 plus b upon 2 comes at this point. So let's say this is x2. Now drawing a perpendicular from the x2, we can see that this is cutting the curve at this point, and here we have got this f of x2. So now we will take this as new selected point and we have to choose one more from the old values, let's say x1 and b. So at this x2, the function's value is positive. So what we'll take the end point at which the function's value is negative, that is x1. So our new interval will be x1 comma x2. So the new interval will be x1 comma x2. So let me write it here, x1 plus x2 divided by 2 will be our next approximated root, that is x3. So let us see if the x3 comes at this point. So this will continue and we can see our interval is getting shorter and we are getting closer to our root point, which is this, let's say. So this is our real root and we are getting closer to this real root. We can get the solution in two ways depending upon how the question is asked. In many times the question is asked to give the answer to the desired accuracy till some places after decimal, or in the question they used to ask you that perform till let's say 5 iterations, 10 iterations and so on. So we'll see how this can be used to solve our equations. So let's see and take an example. So let me erase this. Let me take the example and solve this. So let me take the example as a fx. It is given as, let's say, x cube minus x minus 4. Let's say if the function is given and we have to evaluate the real root of this equation. Now the question could have been given in two ways. Find out the root till correct to 3 decimal places or perform 5 iterations. So let's say in this we are going to perform 5 iterations. So we'll do till 5 steps, right? So we'll do till 5 steps. The first thing, we need to identify the interval of this given equation. So just to find out the equation interval, we can use the hit and trial method. So let's put first 0 into this equation. If I put 0, then this will be 0 minus 4. So this is minus 4. Basically we are concerned about this sign, that is negative. So we have got the function's value 0 at negative. Now we will take another point, let's say 1. So at 1 this will be 1 minus 4. So this will be again 1 and 1 cancel, so that is again minus 4. So again we have a negative. So obviously we cannot choose our interval at 0 and 1 because at both the intervals the value is negative. And as we know that at both the endpoints the signs has to be opposite. So we'll have to find out some more points. Let's say if we take this as 2. So now what will be? This is 2 cube minus 2 and minus of 4. So we can see that this 2 cube is 8, then 8 minus 2, that will be 6, and 6 minus 4. So we have got 2 here. And now you can see that this is a positive value. So we have got 2 points at which at 1 the function's value is negative excuse me, and at other point the function's value is positive. So we will take this our initial interval. We'll select this as our initial interval. So our initial interval, let's say a comma b, comes to be 1 comma 2. So this is our first step in getting the solution with the help of this bisection or Bolzano method. In many cases you will be given with this initial interval into the question, so it becomes more easier, and if it is not, then we'll have to apply this hit and trial method, and then we'll have to find our initial interval. The smaller interval you will take, you will reach the result as early. So this is 1 comma 2. Now let's start. The function is x cube minus x minus 4. Let me take a chart here. I'll create this chart. Let's say if I write here a, then b, and I'll write c, then I'll write f of a, f of b, and I'll write f of c. So I'll create a chart using this. Now initially at the first iteration, so we'll start with our first iteration. The value of a is 1, the value of b is 2, and let's say we are not calculating currently c. Then what is the value of function of a? Currently we are not bothering about this value, we only consider here the sign. So what was f of a? So this is f of a. If you can see, f at 1, this was negative, so I'll simply write the negative. Okay, and then at f at 2, this was positive, so I'll simply write this as positive. That's it. I'll not write the values of the function because I need to only consider these symbols. Now we need to find this c. How we can find out this c? The formula to find out the first approximation is a plus b upon 2. This is equal to c. So how we'll calculate c? C will be calculated by 1 plus 2 upon 3. So we can see that, let me use this space for the calculation. So we can see that this is, obviously we will be using scientific calculator for this. So this will become more easier as we have to do. So this is 3 upon 2, that is 1.5. So directly I can write, so the c is 1.5. So now this is c. And now at this new value, we need to find out f at c. We need to find out f at c. So what is f at c? This is f at 1.5. That means 1.5 cube minus 1.5 minus 4. Obviously, we will be using the calculator, the scientific calculator, to get this value. I already have this value. So f at 1.5, I have, this is at negative minus 2.125. So this is minus 2.125, which is a negative value. We are not actually worried about this, but we have to consider this sign. So this is negative. So I'll write f at c is negative. Obviously, the new point will be selected. So this is a negative. So what will be our second end point? That will be, so we'll take one negative and the other positive. That's it. That is the new point and b. So in the next iteration, our new interval will be 1.5 and 2. Why 1.5 and 2? Just because this 1.5 is giving us a negative functions value, and previously from these two we have this b, which is giving us the positive value. So this is 1.5 and 2. So these are our new interval. So this is our new interval. Now we can see that at 1.5 the function's value is already negative, and at 2 this is positive. Now we need to find out this c. So again the same process will be repeated. The same process will be repeated for the second iteration. So this is 1.5 plus 2 upon 2. So the next is 1.5 plus 2 upon 2. So we can see that this is 1.75. Now this is c is 1.75. So we'll write 1.75. Now we need to find out this f at c. So for that, f at 1.75. This will be 1.75 cube minus 1.75 minus 4. So let me see what is this answer. So this is 1.75 cube. Okay, right. This is this is a minus 0.39062. So we have a negative value here. That is more important. So we have a negative value of this function at 1.75. So we can see that this is a negative value. Again, as we always choose the new value, this is already selected, and from the previous two we will select this positive. So the new two will be C and D. So let's say in the third iteration this will be 1.75 and this will be 2, right? So this will be 1.75 and 2. Okay, always remember the smaller value will always be written on this A column, and the larger value will always be onto this B column, right? So at 1.75 this is negative, and at 0.2 this is positive. Now we need to find out C. Again with the same method we will find out C. So this is just the repetition. Once we have got how we can do the first iteration, it will be easier for you to perform the other iteration. So this is 1.75 plus 2 whole upon 2. This is equal to 1.81. So this is equal to 1.875. 1.875. So now this is 1.875. So now as we can see that this is the value of C, 1.875. Then we need to find out f at C. So what will be f at C? That is f at 1.875. This is 1.875 cube minus 1.875 minus 4. Let's see whether it is a negative or positive. So in this case this is positive. Now this is a positive value. Now you see that this is a positive value now. Now obviously we will select this new one, and from the older one we will have to see which is the opposite sign. So the opposite sign is this. So now we will choose these two values A and C. So now in the fourth iteration this will be 1.75 and the new value will be 1.875. Right. So you can see that we have selected this new value, and from the older we have selected the value which is with the opposite sign. So this is negative, and remember we always write the smaller value onto the left hand side. So let's see what is our new C. So now this is new C is equal to 1.75 plus 1.875 divided by 2. So let me see what is this coming. Now in this case this is coming 1.8125. So this is 1.8125. So the new C is 1.8125. Now let me see that this is negative and this is positive, and now let me check what is the function's value at this new value 1.8125. So we need to find out the function's value, that is f at 1.8125. Let me see whether this is positive or negative. So the function's value of this is positive value. So we have positive sign. We can use the scientific calculator to replace the value into these. We will replace the x with this value. So this is a positive. So new value is again positive. We will select this, and from the older two we need to select the opposite sign, that is this negative. So in the fifth iteration, so this is our last iteration. So this is in fifth iteration, we will be taking 1.75 and 1.8125. So this is our last iteration. So in the last iteration we only need to find out the C with the formula A plus B upon 2, and now you can see that this is 1.75 plus 1.8125 whole divided by 2. So this is coming as a 1.78125. So this is 1.78125. So this is 8125. Right. So this will be our 1.78125. Excuse me. This will be our final root. So that we in the fifth iteration. So this is in the fifth iteration. We have got this as the answer. Obviously, this will be the answer that is given after 5 iterations. So this is the approximated root of this given equation after 5 iterations. So I hope you have understood this concept is bisection method. It is a simple method. Just a quick revision that we need to find out first the initial interval from where at one end it should be positive and at other end it should be negative. Then we'll begin with the initial interval and we'll find out the mid value, that is C, by just averaging these two values. So this is let's say A plus B upon 2, we'll find out C. Then we have to see at f at A, f at B and f at C. The new value will always be taken, that is f at C. We'll always consider this is negative, so we have to choose from these two whichever is the positive. So this is positive. New interval will be B comma C. So this will replace B comma C here, and now we have to just iterate this process till the number of required processes or till number of desired accuracy. In the next lecture, we'll talk about the next method to solve algebraic transcendental equations. Till then, thank you so much.